NetBSD about months ago to work on NPF. I think, I don't know, has any one of you been using NPF here? All right. Okay, good. So I guess FreeBSD and OpenBSD guys. Okay, so about me, I'm a recent computer science grad, and I do mostly system security stuff with NetBSD. And in my free time, I hunt vulnerabilities, doing static code analysis, checks, stuff. Yeah. So, few things about me. The day I learned about phishing attacks was the same day I got phished, and I lost my Twitter account. It was a story in school, and we were told about phishing, how people get people to open links and stuff. And so I think I was there, and one lady reached out to me that she wants me to help her with her beauty pageants, promotion stuff. And I ignored it for days, and she kept on worrying me, and I gave in at a point. I was like, okay, fine. And I asked her, how should I go about it? How should I vote for you? And she sent me a link that I should tap on it and vote for her. So when I opened the link, it refreshed, and it sent me to a new Twitter page that I'm supposed to log in again. I was like, but then I didn't really understand anything, so I entered my PIN and everything again, and the account was gone. I tried reaching out to her, she was insulting me and stuff, and it was sad. So I think since then I decided to become security conscious in the tech space, and yeah, so when I was trying to find the right BSD OS to join, when I heard Net, I was like, okay, maybe it's their network operating system. So I decided to join NetBSD because obviously when I heard about FreeBSD, I was like, are we going to do things for free? Like, okay, FreeBSD, or like, okay, OpenBSD. What am I going to open? So I think it was on the Google Sum of Code page, like 3 OSs. I was like, okay, free. Then maybe I would have to pay if I join OpenBSD or NetBSD. I was like, okay. So, but I was like, okay, I don't care. I'm just interested in programming networks. So let me just join NetBSD. And then I became a contributor to NetBSD, I think about 9 months ago. So we'll be talking about firewalls, and how many of you intensively use firewalls in your home networks? Okay, I guess everyone. I think so. Firewalls have largely evolved over the past decades. Early firewalls use packet filtering to analyze individual packets based on their source and destination address, ports, and protocols. But I think the development of, if you read far, you realize that the development of firewalls was a response to the increasing threats of unauthorized access and malicious activities on networks. So trying to prevent intrusion by people who are not actually allowed to communicate on networks, basically the basic rule of firewall. So if your firewall is not simply doing that, then I don't think it's a firewall. So have they really done a good job so far? I think so, because right now we're able to clearly manage our networks, even though there are still intrusions. People still get into networks, but I think firewalls are doing a great job, yeah. Applications are still breached and stuff, so maybe we try to do a lot of protecting ports and stuff to protect services, but still people still get access to. So we hear about attacks still in this generation. So then what's a good firewall? In my definition, I think a good firewall is a firewall that is able to meet the current needs of rising threats. So as we go on, attackers change their approach, they get faster, they get smarter. I think most of the attackers we have are experts. They know more than we know. I don't know. They know more than the creators know. Currently, there's an exploit in my country where I came from, and you could just be there and then receive a call from someone, and right up maybe after like 2 minutes, and then you realize that all your money in your account is gone. just vanish like that. And you just think about it. And these people are uneducated people. And it's just weird. Like, how are they able to do this? And you speak to one and you realize that they've actually got it, that they've actually relaxed and studied very, very well. So as they are growing, I think we should also grow as security personnel, security professionals. Yeah. So firewalls are security guards, and obviously the security. I think there are some security guards here at BSD Can. Yeah. So obviously they are the one protecting us, but they are not superheroes. Obviously, some people can attack them and beat them, and they will become vulnerable again. I don't know. So then who protects the security guards? If they are being attacked, who protects them? Are we the one going to protect them again? I don't think so. So the security guards need to be protected by the external environment. I think. So maybe the security guard will have to know that he will have to eat maybe heavy food to build strength, proteins and stuff to build strength to fight, and maybe where he will get ammunition from to be able to shoot people who try to intrude and stuff. Yeah. So the environment. So if you relate this to computing and security, we protect the firewalls. As a firewall programmer, you need to not play with secure coding practices at all. It should be key. It should be one of the most important things to actually consider when designing firewalls, when programming firewalls. And actually, we have a language which is not maybe safe, and so many noise about using C and change to Rust and blah, blah, blah. But still, that is the language being used to actually program firewalls. So it's not going anytime soon. It's not going anywhere. It is here with us. So we have to embrace that. And also having a high performance kernel is super. Basically, I don't know of any firewall that's main filtering in user, and maybe there are some you guys who know, but personally I don't know of. And so having a high performance kernel is super important, and we should not play with it. Yeah. So security in the modern world, right now CPUs are fast, very, very, very fast. I think there's research, ongoing research to speed them up, and people are still working to make CPU faster as they get super fast day by day. And then, as I said, attackers are experts, and they get smarter day by day. There are new RFCs coming all the time and says, hey, this is bad. Okay, I'll update it. Okay, now I'm changing it. Okay, stop using this because you can use it to attack this. Okay, now I'm changing it. So we realize that the attackers are beating us every day. They are making our lives miserable all the time, updating stuff, research stuff. So configuration managements are not enough. Ideally, if you have a system you're trying to protect, obviously you have softwares written that you can configure them to do your protection for you. But if you are fighting against an attacker who is very well informed, I do not think it's enough. There's more to it. But if it's not enough, it doesn't necessarily mean it's not useful as well. So obviously, but if you can configure more. So I think most people have firewalls with about 1,000 rules, 2,000 lines of rules and stuff. Yeah. So how pragmatic you can be with your ruling is also important, right? Not just having rules, but how easy you can configure your rules in your firewall. How simple or how simplified you can get your rules. Yeah, and how easily you can understand how your rules are going to be inspected by your packets. And all these things are factors to actually go into. So now let's talk about NPF, the main purpose for today. So at the IP layer, NPF supports IPv4 and IPv6 protocols. It does NATs, you can use it to do NATs, and also port forwarding with destination NATs. So ideally, you can use it to, especially in routers. And now supports layer 2 filter. It's not merged here, but it's completed work, and It's currently under review, but now you get to additionally filter based on MAC address and ether type, basically. And also supports user group filtering. I think that's already in PF, so I'm sure the PF guys will be familiar with it. But with that one, there's a few not so good features about it that I would explain here. All right, and there's an ongoing work. I'm currently mentoring a GSOC student to support NAC 64. I think that's already in PF, so we are finding ways to integrate that in NPF. And so some uniquely good things in NPF in the BSD world. I think the syntactic rule groups are, I looked into PF and you do not have a way to actually group packets based on group rules, based on certain criteria, certain filter parameters. So in NPF, you are allowed to group your rules on, say, interface and packets direction. And so it makes your configuration very easy to understand and very easy to change. So if you have an NPF configuration, basically this is how the structure is going to be like, a group, the group name and the parameters, and you have your rules into it. So a group, the name, and maybe different parameters, and has your different rules into it. So, okay, let me explain what the groups actually are. So in the code, in how it is designed, a group is actually like a rule, but with no BPF filtering mechanism attached to it. The group is just a rule, a filtering rule. It's actually created as a rule. But the rules in the group do not inherit any attributes from the group, and the groups are not strictly bound to one interface, even though they behave as such mostly. And the groups give a hint to the filter logic about the cluster of subgroups it should focus on. So if there's filtering, it comes to this group, the logic gets an idea, okay, what should I do here? Okay, what I shouldn't do here? Okay, maybe I shouldn't go here. Maybe I should go here. So I would explain that further. And there's also a skip to mechanism that NPF uses in the rule inspection. So if, let's say, if a packet is, if there's traffic coming internally and it's supposed to be filtered by a firewall, your group can tell it that, okay, if you pass this group and you go into these sub-rules, check until maybe you find a match for a particular rule in the sub-rule. But if you do not match it, okay, you can go to the next sub-rule. But if you match any rule in it, okay, then you use that to either accept or block the packet. But if you do not match the packet at the group layer, quickly skip all the rules in the sub-rules and go to the next group. So it's more like maybe you leaving home and telling your friend that at 11 o'clock you'll be at 1160. And there are other three blocks. There is 1110 and 1120. So if whoever is coming to look for you and the person gets here, the person quickly knows that you are in 1160. So the person wouldn't waste time going to 1110 and 1120. Quickly will come to 1160. So if he goes to 1110 and asks, is this 1110? No. Okay, he goes to the next one, is this 1120? No. Rather than asking where is, maybe you are called John, where is John? Where is John? In every single room he or she goes to. So groups are, the group mechanism in NPF is great. It helps you organize your rule sets very well, very neatly, and you do not have so disorganized rules anywhere. And it makes packets look up very easy. So when a packet hits your firewall, the group is the first rule. As I said, the group is a rule, right? So the group is the first rule to be inspected. And then the packet inspection against a rule. So the group parameters I think I missed that. The group parameters are, as I said, an interface and direction. Perfect. The interface name and the direction. So you can actually configure a group for all packets coming in, or a group for all packets leaving. And you can also group rules for packets on maybe your internal interface to your home network, or maybe the external interface to the outside world. So, but it's not strictly, they're optional. You can also have a group that doesn't actually match any filter parameter. So then when it comes, it just goes straight to the group and looks for all the rules in the group until it finds a match. And then the rule actually does what it's supposed to do to it. So as I said, if the packet comes and it hits your interface, it checks if the group, say you have, let's say, group on, let's say, WM0 interface, and then it comes and it checks that if there's a group interface stated, then it will go and check if the group interface is the same as the interface the packet is traveling on. If it checks and it's not the same, it's not a match, then it skips to the next group. So if it checks and it's the same, okay, now it goes to the group direction. If the group direction is not the same, so if there is a group direction stated, and the group direction is not the same as the packet direction, then it's not a match. And if this happens, then it goes straight to check that if there's no BPF code. Basically, NPF uses encode, like similar to BPF, to do your filtering and not nested if else. Now, that's different in NPF. So, and then it returns a true to actually indicate, okay, now there's a match. And then it actually blocks or allows your packet based on the rule in the BPF. So, and the other good thing in NPF is that the core filtering logic is encode similar to BPF, and you can also JIT compile your bytecode to native machine code quickly in the kernel to run in the BPF VM. So we can look at simple examples of filtering rules that are used in NPF, and then we understand the whole structure of having a very effective firewall rules in your NPF configuration. So from the top, you can just quickly set your bpf.git to 1 so that you skip interpretation overhead. So that you do not, you can get your bpf.git compiled once and not actually all the time do an interpretation again if there's a rule to be inspected. So say you are trying to maybe have an external interface. This is just an example. I use the loopback interface to just do a simple one for us. And then you have a group external on LO0. And then so you are telling every packet that is coming. If the packet is not traveling on LO0, it should skip this group. It shouldn't even think about coming to this group because none of the rules has anything to do with it. So, but if the packet is traveling on LO0, it is going to look at the rules in this particular group. So, say you have block final from Mac to BSD. So let's say maybe you're trying to do an SSH connection, and it happens on the WM0 interface, and you have your Mac, let's say you're running your BSD as a VM on your Mac, obviously they'll all be in the same local network, and you are trying to send packets from your Mac to your BSD, and it's happening through the WM0, the virtual network interface. So if it is coming, even though you have a block final from Mac to BSD, it's going to skip this rule because you have told it that it has nothing to do with this group. So once it comes and it hits the external, the first group, the packet is traveling on the WM0 interface. It has nothing to do with this group, even though you have configured a rule to block it in this particular group. So then this rule becomes waste. And you will have to quickly, it's mandatory that you set your default group to do what you want it to do. So even if you have a rule like this, and then you are trying to block packets from your Mac to your NetBSD or FreeBSD VM on your Mac, it is going to go straight to the default rule and pass it. But you'll be expecting a block on it, but it's not going to actually inspect it. So when the packet traveling on WM0 gets to here, it quickly checks. The filtering rule on this group says that, okay, you can only come here only if you are traveling on LO0, sorry. But if you are not on LO0, please come to default. And so your intention is to block the packets from your Mac to BSD, but they get passed. So the group mechanism is very key, and it passes at default. So this is a simple encode. It's very similar to BPF. It's almost like it's BPF-like. Yeah, for when it's passing the rule from Mac to BSD. And so if you set your group to be on WM0 and the packet is actually being inspected, this is the way it is going to actually inspect it. So it uses, BPF uses very few instructions. It just uses, and then it also has the accumulator where it loads the most recent fetched data into the accumulator, and then you can use it for any comparison. And you can easily go, and the BPF also has the power to actually fetch data from offsets of the packets, the MBAF that is traveling across the network interface. So we know that if you load, the fetch is always a 4 bytes fetch, a word. A word is 4 bytes fetch on BPF. So if you load the first 4 bytes on your IP header, and as we know, it is the IP version. All right, so it's going to check. So if the packet is coming and it checks the first 4 bytes of the packets, being the IP version, it checks against the IP version you set on the rule. But the NPF has a way to configure. If you set IPv4 addresses on the rule, before it is being passed to the kernel, it quickly knows that, okay, this is an IPv version 4 and not a 6. So it quickly loads an IPv4 address family into the rule. And so when the packet is coming, it's taking the first 4 bytes, offset the index 0 in your MBAF, in the IP header, in the MBAF, and then checks to it if it's a match. So if it checks and it's not a match, quickly goes to instruction 7 to return 0 to say, hey, this is a false packet. So don't process it. It's not what I'm supposed to do. But if it's a match, it is going to instruction 2. And then it is now going to load the data of it's going to load the data 12 bytes offsets the IP header. And that is the, I think, source address there. The source address in the IP header. And here we can easily use a one fetch instruction to get the 4 byte because IPv4 addresses are 32 bits. So you can easily get by a single fetch. And then you fetch it, and then it's stored in the accumulator. And then you do a check to jump if it's equal to. So if what you fetched in the IP header is the same as what you passed on the rule, here being converted to hex to check if they are the same. If they are the same, then jump to the fourth instruction. I think JT for jump if true and J for jump if false. So if they are the same, then jump to the fourth instruction. But if they are not the same, quickly jump to the seventh instruction and it's a false. It's not a match. So I have nothing to do with it. But if they are the same, jump to the fourth instruction. And then now we are about to check for the destination address, where it is going to. So if you load, if the source address matches now, come to instruction 4, and then load the data, 16 bytes, offsets the IP header, and then check it against what is passed on the rule, the address passed on the rule in hex, and then check again. Are they the same? If they are, okay, yes, now go to instruction 6, and then return -1. So a return -1 means that it is a match. But a return 0 means that it's not a match. But this is not a point where it decides to drop or passes the packet. Where it decides to drop or pass the packet is after it has been inspected for it being a match. And then we use the drop or pass packet command to either decide to drop it or pass it. So this is a simple, I think if you add ports, numbers, and all those things, you can able to, it does everything by offsets in the IP header. And the same thing with the TCP header. If you add, if you are supposed to maybe check for the layer 4 protocols and stuff. And so this is an example rule to just look at. A group external on WM0, pass final on from MAC to BSD, and then pass final on from MAC2 to BSD2, and MAC2 to BSD2 maybe being maybe an external communication that happens on maybe like EN5 or something. So if the packet is coming on WM0, okay, fine. It is going to inspect the first line, pass final on WM0, because MAC to BSD happens on WM0. But even if it's coming on WM0 and the first one doesn't match, it is going to the second one. But maybe MAC2 to BSD2 doesn't also happen on WM0, it's a skip. Quickly. But from here, any packet that is coming on EN5 doesn't care about the group external on WM0. It has nothing to do with it, it skips it. And so you can have a rule set arranged in your configuration that you have them so separated from each other and function at a very, 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 very strong performance level. In the sense that a packet will not struggle trying to find a match. Quickly, if you have like 2,000 rules configured, maybe you are using your NPF as a router, you have like 2,000 rules configured, maybe you have one on your route your NPF to home device communication, you have one to NPF to the external world communication. And if the packet is traveling, it wouldn't actually waste time to go all the long way to do all these things. Quickly knows that, okay, here, I have nothing to do with here. I come here. I have nothing to do with it. I come here. If it's an external packet, I have nothing to do with here. I come here, and then so the route it takes to find a match is so short if it is well organized. So let's look at an example of routing with NPF. If you are trying to use your NetBSD as router in your home network, and so you have two interfaces, one for your home network communication and one for the external world communication, and so you set your public interface that you use to the router's public IP that you use to communicate. And then this is a simple home device local IP that you use to also communicate so that you can route your packets from the internet to your home device. And this is an external interface to communicate to the internet. And this is an internal interface to communicate with your home network. So if your home devices are trying to send packets to you, obviously, through the internal interface, and then if you are trying to send, if it hits NPF, the NetBSD kernel knows that, oh, okay, it checks the destination address, this is not for me. I'll have to check my routing table and see where I'll send it. So then it will know that, okay, your external interface is where it's supposed to pass through. And then it is being taken away to the internet. So let's look at simple rules you can actually configure. So in the beginning like this, if you are trying to route, you know that, okay, these are the two interfaces involved. I separate my rules, group X on external interface and group int on internal interface. And then so you quickly know that, okay, I'm supposed to receive a packet from my home device. So that would be definitely on my internal interface, right? So then you pass in final from your local IP3, which is your home device. So any packet that is coming that has a source address of local IP3, you pass it. But the way network address translation works in NPF, I think either FreeBSD or OpenBSD, one of them does the nuts before they pass the packet. One of them changes the addresses before they pass the packet. But in NPF, the packet is passed before, if there's any nuts to be done, it is checked and it is done. So if you are supposed to receive a packet from your home network and route to the internet for your home device, you quickly know, okay, the packet is going to be sent from your home device to me, the router. So, and that will obviously happen on the internal interface. So on this internal interface, pass in final from local IP3. So every packet that is coming from local IP3, which is my home device's local IP, pass it. So after I pass it, then I set a rule to actually pass out final from local IP3. So I think I missed it. Okay, yeah. So after I receive it, I know, okay, obviously I also need to send packets to it, but for that one, I would need to do it on a different, so when I receive it, I would have to pass it to the outer internet, because when the packet hits me, the router, I would need to, the NetBSD kernel will know that, okay, the destination address, maybe you are trying to send to google.com, and then my node is not maybe 10 points, whatever. This is not my destination address. So the kernel sees this and knows that, okay, I'd have to send it to a different interface, looking at your routing table and seeing the default gateway for that particular destination address. And so you know that, okay, then that means obviously the packet is going to leave me and go to the network, to the internet. So I'm going to pass out final from local IP3. So obviously, any packet that has a source address of local IP3, being the packet that came from my home device, it is not yet changed. It's supposed to leave. All right, so now the kernel has told us that this packet is not for us, it is leaving. And so we know that it's obviously going to leave on our external interface, and then we have that one there. So then, after we've passed it, when it is leaving, at the junction at which it is leaving, we rewrite the source address to make the packet appear as if it came from the router, ideally. So hence, you do your map on the external interface and being static, stateless, to not actually worry about sessions and stuff. And then a right arrowed map indicates the source address mapping. So that's a simple natural to see that, okay, now change this address, change the source address to the router's public IP address. And obviously it is traveling on the external interface. So change it to appear as if this packet is generated from the router itself on its public IP. And so when it goes to, say, Google, maybe you are trying to speak to Google, and then the packet is coming back. When the packet is coming back, it's going to come back to the router's public IP. So pass in final to public IP3, because when Google is responding, it's going to respond to the router's public interface. And so when it comes, it is coming to IP3, but the router knows that this packet is not for me. This packet is supposed to go to my home device. And so you have an external rule, right? So when it passes, you know that, okay, at the IP layer, change the destination address quickly, so that when the kernel sees it, the kernel will know that, oh, okay, this address is not for me, and then it will actually easily configure a route. So before that, you also do, and you obviously know that the packet is going to be passed to the local IP. It's going to be passed from you to the local IP3. But that one, I think I missed that too. Oops. Sorry, it's passing from out to local IP3. Sorry. So you know that the packet is going to be passed in to your local home device. And at the point it's being traveled to your local home device, you actually do a NAT. But here, you are not actually going to rewrite another new NAT rule because we can quickly just simply do a bi-directional NAT so that it will now know, okay, there's a communication between this local IP, me, the router, and the internet. So I can quickly just change the local IP address and the public IP address bi-directionally. If it's coming from the internet to the device, change the destination address. If it's going, change the source address. And then you have your simple binary rule here. And then, so then when you have this flowing through, you set a mandatory default group to block all packets on your NPF NetBSD device. And so this is a simple way you can use NPF to route, to use your NetBSD as a router in your home network. And I think this makes the rule very organized and easy to configure, I think easy to understand, very appealing to the eyes, in my opinion.
Sorry, quick question.
All right.
On the internal interface block, one of those should be passed out, right?
Yeah, I meant pass out to.
You have the same rule.
Yeah, I think I made a mistake with that. I corrected it. Pass out final to local IP3. And so you can also do port forwarding with it. Ideally, if it is coming on the external interface and maybe you don't really want to expose you want to receive it on your port there and actually transfer it to a different port on your local IP3. You do a destination. So I think the left arrow indicates the source address or port change, and the right arrow indicates the destination address change. So I'm sure it is not difficult to configure. So NPF, the performance in NPF, it's great for me in the sense that you have short local routes for packets if you are trying to find a match. And then the use of encode similar to BPF and BPF JIT supports, you can easily JIT compile your encode into native machine code, and you get less instructions to use and reduce interpretation overhead and branching in the CPU and stuff. Yeah. So at least you get some performance boost, ideally. So recent work that I've done, I've been able to integrate layer 2 filtering in NPF, and you can combine it with layer 3 filter. Per research, it's not really safe if you do, because right now people can easily change MAC addresses, MAC address spoofing easily, and they can bypass your internet. So, but it can also help if you want to actually easily block packets from a particular, because obviously if you do a TCP dump, mostly, and then you try to look at the internet header, you realize that packets transmission is mostly just between MAC addresses, like from here to here on the same network, right? So it can easily be an additional tool for you if you want to do several things. So right now we also inherited the same grouping mechanism, right? So groups for filtering a link layer are marked with layer 2, and then rules to be inspected in layer 2 groups are marked with ether token after action indication of the rule. And then layer 2 default rules are mandatory when you include a layer 2 rule in your configuration, and layer compatibility is checked to ensure that the right rule is placed in the right group. So you cannot actually write a layer 3 rule in a layer 2 group. It will be flagged and not pass to the kernel. And you can also not pass a layer 2 rule in a layer 3 group. So the operation in the kernel, we use a pair interface Etherpay field filtering hooks. I think with the IP layer, it is shared, right? I think even with PF, it is shared. The hooks are mostly shared, and then we also use the NPF cache utility. So if the packet comes and you would like to do other things with the header fields, you don't have to actually go and refetch them again. You have them stored in the cache and then quickly do a lookup. And then no contiguous method access checks in MBAV. I think with MPF in the IP layer, we do a lot of MBAV contiguous checks to actually be sure that we can get the IP header accurately. I think sometimes you can get some part of the maybe 10 bytes of the IP header in the first MBAV and maybe the rest of them in the second MBAV chain. But with Ether header, it's almost 100% rest assured that you are going to get it in the first MBAV and not the second. It can never appear or get split across different MBAVs. So I decided to not do, but it's well tested and never breaks. And so we also employ BPF inspection in the Ether header, connectionless, does not communicate with upper layers, no memory store of data for inspection. We do not use a memory store in layer 3 encode inspection. So if you can have a simple layer 2 rule. You have your source Ether address to be maybe from one device on your home network, ACBC 0D, AZC 67D, and maybe a destination AB68, AD64. These are just random numbers I use, but and then you have a group X in WM0. So you mark it with layer 2 in your configuration to tell MPF that, oh, okay, inspect this at either Ether input or Ether output, not IP input or IP output. So you pass Ether to indicate that, okay, this is a layer 2 rule from the source to destination and then type. So I decided to use EX syntax to 0080 for IPv4. And I think I'm also thinking about trying to change for just IPs. So the Ether type, you can just add Ether IP or Ether IP6. But the rest, I think there are lots of Ether types. So it won't really be fair to the others to just use IP. So I decided to use EX00. And so you use the 2 bytes Ether type field, and then you check. So when the packet comes and it's on the layer 2 rule, it's going to inspect it at the Ether header and do your checks and with the same BPF format. But here you realize that the Ether, the MAC address is not 4 bytes, it is 6 bytes. So you cannot fully fetch it in just a single fetch. You would actually need a load and a half word load and a full word load. So, and these are things, if you do not take care with NDNS, you can easily mess up if you do not fetch it very, very well. I think it's very handy, but it's also very easy to go by. So you load, I think, and we have just 3 fields in the Ethernet header, the destination MAC address, the source, and the Ether type. And being 14 bytes field, 6 and 2, very easy 6 instructions. So you load the data 0 bytes offset the Ether header, and then you compare it with 4 bytes of the 6 bytes address you set on your rule. And then you also load the data. By this one, you are going to do a half fetch. So it's going to just take the 2 bytes, the rest of it, and then compare with also the 2 bytes of the first MAC address that you set on your rule. And then it's going to load, and then it checks if it's a match. If it's not a match, quickly go to instruction 11 and return 0. Or if it's a match, go to instruction 2 and continue the inspection. So the same way happens, and then if you also, so it does a fetch, a full word fetch and a half word fetch per MAC address, and then checks, inspects for each of them if there's a match continuum. And then after that, it fetches the data 12 bytes offset, but ether type is 2 bytes. So no need to do a full word fetch, just a single word fetch is enough, and then you are done with what you're supposed to do, and then it checks if it's a match. If it's not a match, it goes to the defaults to check if you're actually supposed to pass packets by default or block packets by default in firewalls. Yeah. And so I also integrated user group filtering. I think it is also in other firewalls. It's in PF and it's in PF. I looked at how PF did it, and basically that was the inspiration that I used to do this. But the main filtering decision is based on the UID or GID pass on rule. So if you are trying to block, maybe you have a Unix daemon maybe created by a particular user, and you don't want any packet to hit it. You don't want it to send or receive packets quickly. And maybe just know the owner of that daemon process, and then look at the UID. You can also pass it by name and then block all packets going to that particular process. So, and then check the effective UID and effective GID of sockets used in the network communication. So it's not checking the ID of the process, the lightweight process rather, by checking the ID of the socket used in the communication. So even if you are not the one who fired the socket, but you are using the socket, but you are a different process, the rule will be for you. So this is a very funny feature in BSD firewalls that I would also want to talk about. The rule will be for you. So an example is you can have a simple one to block final from Mac to BSD, use a Joe group BSD can. So on your machine, if this packet is traveling on L00 and it comes here and you realize that, okay, there's a communication between your Mac and your BSD on L00, and then it looks for all users in group BSD can and checks if Joe is part. So if Joe is the one in BSD can who actually fired that socket, who is the owner of that socket, then it's actually going to block the packet. But if Joe is not the owner, it's going to pass it. So it's more like a reverse action. If Joe is the owner of that socket, it's going to block it. If Joe is not the owner, it's going to pass it. And then, but if Mac to BSD happens on a different interface, it's going to come straight to the default rule and it's going to pass it. So the limitations of this design is that we know Unix servers are designed to bind on root, and then later unprivileged users inherit the connection. If let's say a client is trying to communicate with the server, and then the root accepts the connection, the accept socket is being handed over to the unprivileged user. And so, but the thing about Unix servers are that the socket's credentials do not change. So if you try to do this ruling idea with Unix servers, you are going to get confused because it's not going to be effective, because I don't know if there will be a need to actually change the way Unix servers actually behave with socket inheritance. But I think if like normal SSH, if you want to do user protection with SSH, you can quickly go to SSHZ config and allow a particular user or deny a particular user. But I was thinking about it that now if we can able to find a way for this feature to also work with Unix servers, you can have a single way to actually protect servers on your machine, different servers on your machine by using firewall rules. Maybe you have this server bound on port, this SSH bound on port 22, and then packets that are coming to the address, and at port 22, you can actually configure on a firewall rule that, hey, block, maybe you want only this particular user to share resources and this particular user should not share any resource. You can actually use a firewall rule, but that was what I was going towards to try to see if it's going to work, but because of the design of Unix servers, it does not really work. So for now, it is very effective with normal user daemons, maybe things you create by root or non-root users, and then you would like to block packets to them based on the rule. But if you want to use a Unix server system, and then you know that obviously when the connection is accepted and you check your net stats, you realize that it's now a new user that is firing the traffic, and you get deceived to think that this is actually going to work with it. Because the sockets that has been inherited, the credentials doesn't change. It still remains a root socket in this lifetime. So as I said, the Unix servers are bound as root, and accept sockets are inherited by unprivileged users. But the credentials of the accept socket forever remains root. And so you can only get effective filtering on only the root user. So even if you have a Unix server, and then you block packets to user A, you block packet to user B, you pass packet to user C, it is going to assume root. So it's even going to see it as you are saying block on root, block on. Everything should be root because the packets, the sockets that are being used remains root sockets. So as I said, we know that Unix servers bind to privileged ports number that are less than 1024, and for like a normal SSH application layer manages user authentication, authorization, and session management before they are being handed over. The kernel handles pre-root, listening sockets, connection establishment, data buffering, and stuff. And so with a common case like SSH, as I said, SSH passes server configs and load keys and certificates as root. SSH listens on port 22 as root. And then the clients connect, SSH accepts connection requests on listen socket as root. Returns in a fork child to handle established connections, still as root. Creates a new session as SSH session, still as root. But when it happens, it is being forked and handed over to an unprivileged user. But then you might think that is the unprivileged user now owns the socket. No, the socket still remains a root socket. And then so the SSD session negotiates encryption and key exchange, still as root. So you can match blocks and deny user checks in both process. And then session terminated midway if client is to be denied access to files through SFTP. And then authentication is completed and post-auth authorization follows each user to be allowed access. But then the process drops privilege and the session starts, now as unprivileged user. But as it has dropped privileges and now is now a session, the unprivileged user gets to maybe if you are so sending or you are so receiving. But the socket that is being used is still a root socket. So that is the limitation we have. Right? And I think it's not the same in NPF. I think in PF, using the socket, it's the same. So fun future project that I'm looking on to have a firewall feature that can give cross-database protection to Uniserver. If it's not sensible, then I'm not going to stress. But if you can have a feature like this, I think it's going to be great. Yeah. Thank you. Yeah?
Emmanuel, I saw something on one of the earlier slides that I think was a typo, but it gave me an idea to ask you a question about potential optimization.
Okay.
On the slide where you were doing the group on WM from Mac to BSD, the individual rules you had pass, in, on, but then you didn't name the interface in the line. I think the parser requires the interface name, am I right?
No, if you set the interface on the group,
okay, no.
setting it on the rule is not compulsory.
Okay, so I didn't realize the parser would allow that. And then, so it wouldn't insert BPF code to do the check a second time.
No, it would insert the BPF code when it's the rule, but I already set a BPF code when it's a group. The group
So
is just
do
to
it
check.
once for the group and not for the individual rules.
Exactly. So if you set the interface on the group, the check is just checking for interface match and direction match to actually tell the filtering log, okay, go here and go and look for the rule you are looking for. And that is when it's going to do expression based on the BPF. But setting them are optional. It's not compulsory, but on the normal rule, so hence, if you set a group on the interface name, the packets are assuming that all the rules in this group are on WM0.
Okay,
Yeah.
so the optimization is already there.
Yeah, totally.
It would be interesting, the last thing you were talking about, it would be interesting to think about whether we could pass a label on the socket and use the capabilities framework to say, okay, firewall said this was only supposed to be allowed in for a particular user ID, and it came in on a socket that's owned by root.
Okay.
But later on, the capabilities framework could say, we're not allowed to deliver this data to anybody except the user ID that the firewall said it was allowed for.
I think that would make sense. I think that'll work. All right, I'll look into it. All right. So no more further questions, I guess. All right, thank you for your time, and thank you for joining my talk.